All right, let's dive right into this explainer. Today, we're unraveling the sheer mechanical wizardry happening under the hood of the world's most exciting cars. If you've ever heard that distinct whine of a spooling turbo and wondered, what kind of physics-defying plumbing actually makes that happen? Well, you're absolutely in the right place. We're going to break down exactly how these incredible systems force-feed engines to produce just massive amounts of power. Now, right off the bat, there's a question that catches a lot of people out. Seriously, even usually reliable sources like Wikipedia or ChatGPT constantly get this terminology completely wrong. You'll hear twin turbo and biturbo thrown around by car enthusiasts and even aftermarket parts manufacturers, like they're just interchangeable buzzwords. But from a strict engineering standpoint, they represent two fundamentally different approaches to generating boost. So the absolutely crucial point to remember here is that a twin turbo is a parallel system. It splits the work. A biturbo, on the other hand, is a sequential system. It passes the baton. That right there cuts through a lot of the industry's marketing jargon. A true twin turbo setup uses two identically sized turbines working at the exact same time, right in sync. A biturbo system operates sequentially. So usually you've got one smaller turbo waking up at low RPMs and then a larger one taking over when the engine is really screaming. So here's our roadmap for navigating all this complex plumbing today. We'll start with the twin turbo terminology trap, move into the Goldilocks turbo compromise, then check out parallel systems doing double duty. After that, sequential systems going one by one, compound systems for maximum boost, and we'll wrap it up with innovations and weak points. Let's get into it. Part 1, the twin turbo terminology trap. We really need to formally address this trap because it catches so many automotive enthusiasts and DIY mechanics. Getting this terminology right is absolutely the foundation of understanding the mechanics we're about to look at. Which brings us to part 2, the Goldilocks turbo compromise. Because honestly, to understand why we even need two turbos in the first place, we first have to look at the inherent problem with using just one single turbocharger. It all comes down to the physics of exhaust gases and the physical size of the turbine. And this perfectly illustrates that Goldilocks dilemma. Engineers basically had to find a way to get both that instant off-idle response and massive top-end power without completely choking the engine. See, a big turbo gives you massive power, but it requires so much exhaust heat and energy to spool up that your engine feels completely dead and laggy until you hit around 4,500 RPM. But, okay, if you throw a small turbo on there, sure, you get a wonderfully snappy response right at 1,500 RPM. The problem? By the time you hit those higher revs, that small turbine is physically choking the engine's exhaust flow. You just stop making power. You really need a system that's, well, just right. Okay, part 3. Parallel systems, double duty. Let's look at our first major solution to this problem and see how a true twin turbo setup actually works in the real world. By essentially splitting the engine right in half, like having one turbo for each side of a V6 or a V8, you drastically shorten the exhaust piping. That saves space and hugely improves response time. Honestly, think of it less like a single engine with two turbos and more like two separate 3-cylinder engines living together as roommates. Each one gets its own perfectly sized turbocharger, and they just work together in perfect harmony. From an engineering standpoint, this is a lifesaver. It solves some major packaging headaches, because each turbo sits right next to the exact cylinders it serves. Take the Nissan GT-R, for example. It's a V6 engine, where each bank of 3 cylinders just feeds its own turbo. And even inline engines use this, like BMW's famous N54 straight 6. BMW basically just grouped the front 3 cylinders to feed one turbo and the back 3 to feed the other. It's clean, it's efficient, and it significantly cuts down on turbo lag, simply because the exhaust gas doesn't have to travel through miles of complex piping. But, as great as that is, the original compromise hasn't completely vanished, right? You've really just divided it. You still have to choose the physical size of those twin turbos. If you make them too big because you're chasing massive top-end speed, you're still going to suffer from sluggish low-end response, which naturally leads us to our next brilliant engineering solution. Part 4, sequential systems one by one. If parallel systems split the engine, sequential turbocharging acts much more like a dynamic 1-2 punch. This is where we really start manipulating exhaust flow dynamically while you drive. This specific piece of automotive history was actually invented to solve a scary problem: getting rid of that terrifying, sudden onslaught of boost that earlier turbos were notorious for. It was all about delivering power much, much smoother. Porsche realized that by using a really complex system of valves, they could control exactly when and how the turbochargers received that exhaust gas, which created this beautifully linear power curve. Looking at this step by step, It's brilliant. It gives you that instant low-end torque feeling, and then just seamlessly transitions into a relentless high RPM push. Here's how. At low RPMs, the engine just isn't producing enough exhaust to spin 2 turbos, right? So the system forces literally 100% of the exhaust into just 1 turbo, usually a smaller one. Boom, it spools instantly. Then, as your RPMs climb and you start generating massive amounts of exhaust gas, a bypass valve gradually opens up, bleeding all that extra exhaust into a second, much larger turbo. Once that second turbo is fully spooled and ready to go, it takes over the heavy lifting. The catch? Well, while a sequential setup gives you an incredibly broad power band, you're still fundamentally limited by the maximum pressure of the single largest turbo in that system. Because both turbos ultimately just feed their compressed air straight into the engine's intake manifold, your absolute ceiling for boost is just whatever that secondary, larger turbo is rated for. Plus, the maze of vacuum lines, bypass valves, and solenoids required to actually make this switchover happen seamlessly, it is incredibly complex and super expensive to manufacture. All right, part 5, compound systems maximum boost. This brings us to the absolute most hardcore approach out there, where the lines often get super blurred on automotive forums. Get ready for some really fascinating fluid dynamics. I want to make this crystal clear right now. All compound systems are sequential, but not all sequential systems are compound. In a standard sequential system, both turbos feed the engine. But in a compound system, the large atmospheric turbo breathes in fresh air, compresses it, and then feeds that already compressed air directly into the intake of the smaller turbo. Let's really dive into this physics trick because it's so cool. Since the smaller turbo doesn't know the air is already pressurized, it just compresses it again, creating absolutely massive, mathematically multiplied boost. Think about it. If the big turbo sucks in air and doubles atmospheric pressure to around 29 psi, it then shoves that into the small turbo. The small turbo, just acting like it's doing its normal everyday job, takes that 29 psi and doubles it again. Suddenly, you're pushing nearly 60 psi into your engine. It is an absolute monster of a setup. But, and this is a big but, because this generates just incredible amounts of heat, this setup is almost exclusively reserved for heavy-duty diesel engines. See, when you compress air, you heat it up. When you compress it twice, you heat it up so much that if you tried this on a standard gasoline engine, that blistering hot air would ignite the fuel before the spark plug even fired. That's an engine-destroying event called knock. Diesels, on the other hand, rely on heat to ignite their fuel anyway, which makes compound turbos their absolute best friend for things like heavy towing and drag racing. Finally, part 6, innovations and weak points. Now that we know how these systems actually work, let's look at how automakers somehow fit these monsters into cars and, what happens when they break. Because all this pressure and heat definitely requires some serious engineering. Look at modern packaging, like BMW's N63 V8, for instance. They put the turbos right inside the valley of the engine, creating what's called a hot V configuration. This drastically improves thermal efficiency and pretty much kills turbo lag. Traditionally, the intake is sitting on top of the engine and the hot exhausts are routed on the outside. Well, a hot V reverses this completely. The intake comes from the outside and the exhaust dumps directly into the middle cavity, literally the V of the engine, where the turbos are just sitting there waiting. It makes the exhaust travel distance incredibly short, which spools the turbos almost instantly, all while keeping the overall engine package super compact for modern sports cars. Of course, these systems are incredibly complex, and when parts like actuator valves fail, a turbo can easily spin completely out of control, hitting past 360,000 RPM, eventually tearing itself apart. We are talking about turbines spinning at 6,000 revolutions per second. That's actually much faster than the turbines inside a commercial jet engine, and it's doing it in 800 degrees Celsius exhaust gas. If a wastegate, which is essentially a pressure relief valve, gets stuck shut, all that exhaust just keeps forcing the turbine to spin faster and faster until the bearings literally shatter. And that right there is exactly why maximizing efficiency without completely sacrificing drivability relies so heavily on external wastegates and massive intercoolers to keep everything safe and dense. You absolutely have to bleed off that excess exhaust pressure to protect the turbos from overspeeding. And you have to cool down that highly compressed, superheated air before it enters the engine, so you get a nice, dense, oxygen-rich charge for maximum horsepower. It really is a fascinating mechanical ballet happening right under the hood. From the elegant simplicity of a parallel setup to the brutal multiplied pressure of a compound diesel rig, twin turbos represent the absolute pinnacle of internal combustion performance. But, as engines get smaller and the world shifts toward electric motors that offer instant torque without a single moving valve, one has to ask, Are we looking at the ultimate perfection of the combustion engine? Or are we just witnessing its final, beautiful, and highly pressurized gasp? Definitely something to think about the next time you hear a turbo spool up. Thanks for joining me on this explainer, and keep learning.